welcome back. What electric motor should you choose for your project? In a different video we already saw that if you just look at the vehicle motors, electric motors are vastly superior to gasoline and diesel engines. They are much lighter and cheaper. They need no maintenance, and most importantly, electric motors are 3 times as efficient. But which electric motor is the best? To answer that question, you can look from many different perspectives. Electric engineers have dozens of ways to classify the motor, which can be utterly confusing. Mechanical engineers look at properties like size, weight, and maximum torque. Practical builders look at things like availability, simplicity, and robustness. Economists and business people could be interested in purchase price and efficiency. And finally, people interested in the environment are often interested in the use of scarce earth metals and efficiency that is pertains to CO2 emissions. Covering all motors and all angles is impossible. So we will discuss on the 3 types of electric motors used in almost all electric vehicles. While making this video, I found that there are literally dozens if not hundreds of ways to classify electric motors. But if you look at literature of electric vehicles, there are only 3 types of drives that are widely used. That is why we will focus on the induction motor, the permanent magnet motor, and synchronous reluctance motor. Before we proceed to motors used in electric vehicles, let me start my explanation with the classic and simple DC brushed motor that you may know from high school. This motor has fixed part called the stator because it is static that contains magnets. It also had a rotating part called rotor because it rotates that contains electric coils. Stator fixed and rotor rotates. Got that? When you connect the coil in the rotor to the direct current produced by battery, the current from the battery would produce a magnetic field in the rotor. The interaction between the magnetic field from the electric coil and that from the permanent magnets in the housing or stator would lead the rotor to turn. After turning a bit, the magnetic field in the rotor would start to get aligned with that in the stator so that it doesn't turn anymore. But after that happens, the commutator switches the polarity of the connection between coil and battery. The reverse polarity leads to a new magnetic field, and the rotor will keep rotating. A lot can be said about these motors, but we won't, because they are no longer used in commercial electric vehicles. That is largely due to brushes needed for commutator to work. These brushes can malfunction and cause sparks. They must be regularly replaced and they lead to loss in efficiency. They also need starting mechanism to avoid burning out. A better alternative was invented by Nikola Tesla. This AC induction motor, or induction motor for short, needs no permanent magnets. Instead, the magnetic field is produced by a current that flows through the windings in the housing or stator. The magnetic field from the stator will induce, hence to the name, a voltage and current in the windings of the rotor. This is in turn leads to a rotor producing its own magnetic field. And this magnetic field will make the rotor turns so as to align itself with the magnetic field from the stator. Now Nikola Tesla had a second trick up his sleeve. He connected the stator to alternating current, which means that the magnetic field in the stator was also alternating. Actually, if you do it cleverly enough, you can create so-called rotating magnetic field, or RMF, and the rotor will follow this rotating magnetic field in the stator without the need of commutator with brushes. See the advantages? Since the rotor follows the rotating magnetic field only after it has created an induced electric field itself, it is always lagging behind a bit. The amount that the rotor lags behind is called slip. This slip causes the rotor to always be out of sync with the rotating magnetic field a bit. That's why an induction motor is called asynchronous motor. The first AC induction motor ran at constant speed, but later it became possible to vary the frequency of alternating current of the stator using so-called variable frequency drive or VFD. Using the VFD you can vary how fast the magnetic field turns by varying your alternating current or AC frequency. Other names for VFD are variable speed drive, adjustable frequency drive, AC drive converter. It's been very successful. I estimate that in 2017 over 90% of industrial motors were induction motors. It was also used in the first range of cars from Tesla Motor Company. The induction motor has many advantages. The most important may be that it's so very simple to construct and also has the lowest tracker price because no permanent magnets, no brushes, no position sensor, no starting mechanism. Speed control is easy. You simply control the frequency of alternating current, but there are some disadvantages. The induced current in the coil causes efficiency losses. The induced losses mean induced heat in the rotor, and thus the need for cooling the rotor. It is also not the lightest or most compact electric motor. Recent advances in material science have made it possible to produce very powerful magnet using neodymium or some other materials. If we construct a rotor with permanent magnets, we no longer need to induce a magnetic field in the rotor. The magnets have already placed in there. This avoids losses and heat development in the rotor. Because all of these permanent magnets motor are currently the smallest and lightest electric motors you can buy. And because the rotor is already magnetized, it is always in sync with the rotating magnetic field. That's why permanent magnet motors are also classified as synchronous motors. Often the rotor with permanent magnets on it runs at outside. This is called the outrunner. An outrunner can deliver higher torque at lower speed. Sometimes the rotor and the permanent magnets run at the inside, and this is called, you guess it, an in-runner. An in-runner can quickly spin up to high speeds. So when high speeds is not a problem, an in-runner can provide the same power in a smaller, lighter, cheaper package. The permanent magnets motor is increasingly used in all kinds of high-performance applications. Electric vehicles are no exception. And although I cannot statistically prove it yet, it seems more and more electric vehicle manufacturers are replacing induction motor with permanent magnets motor. A good example is Tesla. Although the company is named after the inventor of induction motor Nikola Tesla, its new model uses permanent magnets motor. The picture shows the Tesla Model 3, and it's also true for the new Tesla Semi-Truck. The advantages of permanent magnets motor are that it is lightest and smallest motor. It's also the most silent and efficient motor. The biggest disadvantage is that it needs these scarce earth metals, and they are expensive. They are also a bit more complex to run, requiring position sensor, starting mechanism, and more advanced controller. A recent development in a motor that tries to combine the best of both worlds. It has the rotor that contains metal that is formed in such a way that wants to align itself naturally to surrounding magnetic field, so it doesn't need to produce its own electric field through induced current like induction motor, and this means less losses, and it doesn't need permanent magnets, which makes it much cheaper than permanent magnet motor. This bestows the synchronous reluctance motor with some important advantages. It has high torque and efficiency, especially at higher speed, that is comparable to permanent magnet motors. It does not need permanent magnets, which makes it more rugged, cheaper, and better for environment. However, it also has some disadvantages. Efficiency at lower speed can be a bit lagging compared to a permanent magnet motor. There is higher inherent noise and torque ripple. However, as the rotor design improves and especially as advanced motor controllers and algorithms improve the noise and torque ripple, this motor might become almost as good as the permanent magnet motor without all the drawbacks of induction motor. So it could indeed become a motor that combines the best of both worlds. Talking about combining the best of both worlds, the Tesla Model 3 is not simple permanent magnets motor, but so-called permanent magnets assistant reluctance motor. I made a separate lecture only for that, to get how intelligent the concept is. Let's sum it up. If reliability and striker price are your main concerns, look no further than induction motor. But if you have other concerns as well, there are better alternatives. If all you care about are maximum performance in terms of size, weight, and efficiency, the permanent magnets motor is your best bet. On side note, even though permanent magnet motor is most expensive one in this comparison, it is still much cheaper per kilowatt than conventional gasoline or diesel motor. But if you are looking at the best compromise of all aspects, and if you are not afraid of advanced controllers, there is a good chance that the synchronous reluctance motor is the best choice for your application. Synchronous reluctance motor will improve more and more through advanced rotor design and controllers that minimize torque ripple and dust noise until they match permanent magnet motor performance at the cost and reliability that matches the induction motor, maybe assisted by small permanent magnets.